record. Good morning, good afternoon, or good evening. This is about my presentation on electric batteries and critical materials, geopolitical analysis. So, as you know, batteries are a core element of electric vehicles. They account for about 50% of the vehicle's production cost and are made of rare earth and minerals. The electric vehicle uses 4 times much more minerals than traditional cars, around 200 kilograms more than the traditional combustion engine vehicle. The electric car also needs a more extensive set of minerals compared to the combustion engine vehicle. Contrary to oil and gas, these minerals are not widely spread globally, but are concentrated in a limited number of countries. For instance, in the cases of lithium, cobalt, and rare earth elements, the world's top 3 producers control well over 3/4 of global output. Their demand is growing with the rise of the electric car and the progress in the energy transition towards net zero emissions in 2050. According to the International Energy Agency, a concerted effort to reach the goals of the Paris Agreement would mean a quadrupling of mineral requirements for clean energy technologies by 2040. To hit the net zero globally by 2050, an even faster transition would require 6 times more mineral inputs in 2040 than today. This is a huge increase. In particular, lithium demand would grow over 40 times by 2040, followed by graphite, cobalt, and nickel, which would grow by around 20 to 25 times. So this is really a huge surge in demand. As I explained in a previous article, this surge in demand will not be matched by a proportionate surge in supplies, at least not immediately and not for all minerals. This imbalance between supply and demand is already occurring and has the following consequences. First, the relative scarcity has triggered a global scramble for critical minerals and components that involves mining companies, battery, and car makers. Second, there is a substantial increase and volatility of minerals prices that already spills over to the prices of electric cars. Tesla raised its retail prices for its car between 5 and 10% and has decided to switch to lithium iron phosphate batteries, which cost about 30% per battery cell, less than their nickel and cobalt rich counterparts. VW has done the same, but their most significant drawback is lower range. Cost parity with internal combustion engines may not be reached for mid-range EVs by 2025. This is the third consequence that could dampen demand for electric cars. 4. According to Luca Di Meo, Renault's CEO, the persistent supply chains crisis mean that the game has changed and that car makers have to play by new rules, which would make them more reliant on the efforts of energy and mining companies. 5. The shortage of minerals explains why significant countries and regions have adopted lists of critical materials and raw material procurement strategies. China, the USA, the UK, and the EU are developing more bilateral trade agreements and supporting their mining companies in making deals in mineral-rich countries. 6, they are also trying to develop local mining and local chemical capacities to refine raw materials and the main elements of the battery value chain in their territory. The COVID-19 pandemic and the new Cold Wars have added new concerns about the fragility of global value chains and the overdependence on a too limited number of supplier countries. So there is a shift from a purely neoliberal approach where private initiative and free market competition come first to a more managed form of capitalism where public authorities play a more proactive role. Policies of nearshoring or even relocation are adopted to shorten the supply chains. Our contribution focuses on this last aspect. It calls for an international political economy approach that primarily prioritizes geopolitics and public policies. My presentation has 2 objectives. Firstly, I estimate the concentration of minerals and battery components imported by the EU and the USA to have a more precise idea of their potential vulnerability. The lower the diversity of suppliers, the higher the risk of disruption of supply if one of them is seriously hit by a shock. I calculate the Herfindahl-Hirschman index to estimate the degree of concentration of imports for selected minerals and battery components. I use the UN Comtrade data at the 6-digit level. Secondly, I present and discuss briefly recent attempts to develop mining and refineries of critical materials in Europe and the USA. I show how difficult it will be to reduce dependencies on foreign supplies by creating local supplies of critical materials due to the social and environmental issues. So let's see first the risky dependence on critical minerals of the EU and the USA. As I said in this presentation, I used the Herfindahl-Hirschman index for the import of 6 critical minerals and materials for battery production: lithium, graphite, copper, manganese, nickel, and cobalt. Whenever possible, I look at the raw minerals, processed chemicals, and refined compounds. I also calculate the index for the imports of lithium-ion cells and batteries. So some words first about the Herfindahl-Hirschman index. It is, in this presentation, an index on imports, and it is calculated as the sum of squares of the market shares of all importers of J countries in the total EU imports or in the total US imports. To explain how it works, let's take the example of the EU. I list, for instance, all the imports of the EU on, say, unprocessed lithium, and then for each suppliers, I calculate the square of the market share of, say, Indonesia in the total EU imports of lithium. Then I take the second supplier country, say China. So I square the market share of Chinese supply of lithium to the EU, and then I take the third country and I do the same. And finally, I sum up the whole square market shares of all the suppliers of unprocessed lithium to the EU. And the sum, the total, will give me the Herfindahl-Hirschman index for the supplies of unprocessed lithium to the EU. And I do the same for all the minerals and materials involved for the EU. And then I do the same for the US. So the values of the Herfindahl-Hirschman index range from 1 divided by J, when there are J suppliers, to 1, with 1 being absolute concentration, when all imports come from one country only, and a value close to 1 divided by J, in practice close to 0, when imports come from a large variety of J countries. Another interesting property of the index is that the inverse of HHY can be interpreted as the equivalent number of suppliers in the EU or the USA, where all countries play a symmetric role. So now that we all know what the index is, I just want to add that I follow a recent European Commission report published in 2021, which considers that a country or a region is dependent when the index is superior or equal to 0.4, which implies that the EU or the USA are then considered dependent when their imports originate from mainly 2.5 countries, or in practice 3 countries or less. In the literature, you will find usually that a value of 0.3 for the Herfindahl-Hirschman index is already considered high, and that beyond 0.3, the country or the region will be considered dependent. But I use a more conservative value of 0.4 to be on the safe side, but it means that a value between 0.3 or 0.4 may be considered already significant. And as I said, I use the UN Comtrade with HS code at the 6th digit. So let's see some results for the different minerals which are called ore, such as copper ore, or materials when this ore has been already processed. So, for instance, lithium carbonates or lithium oxide and hydroxide are the first stage of processing of lithium, and the second stage, which then will be used to produce elements of the cells, such as the cathode or the anode, will be refined lithium chloride, refined lithium fluoride, or refined lithium alkali. We can see that for all these processed materials, we have a different EU Herfindahl or US Herfindahl index. I don't have time to go to all of them. It would be too long and would require detailed explanation. I just have underlined the values for which the Herfindahl index is above 0.4, and you can see that it happens several times in the table. So I would like to just summarize the results. Although the EU and the USA are not dependent on cells and batteries as such, we can see that the index is very low for cells and battery, 0.2 for the EU, 0.12 for the USA. Nonetheless, the EU and the US are dependent on at least 6 of the 15 materials, which reveals a high level of risk. 2 additional materials have indexes between 0.3 and 0.35, which I said are relatively high. Both the EU and the USA are not dependent on unprocessed lithium, but are dependent on lithium carbonates, which are one of the first stages of processed lithium, and they are also dependent on further stages of the refinery of lithium. Both countries are dependent on manganese and cobalt ores, and the USA is very dependent on one country only for copper ore. For cobalt oxides and hydroxides, the EU is very dependent on almost one country. And for the ease of language, I will consider hereafter the EU as a country. When we look at the geographical origin of the dependence, and again, I'm just giving some results for unprocessed lithium, lithium carbonates, and lithium oxide and hydroxide. But in the paper that I have uploaded on the JAPISA website, you will find the full list of dependence and their geographical origin for the 15 minerals and materials involved in the production of batteries. So just for this short view on the geographical origin of the dependence, you can see that China and Russia come several times as a significant supplier, for instance, for lithium oxide and hydroxide. Russia accounts for 40% of the supplies to the EU, China an additional 12%, so it means that the EU depends on Russia and China for 52% of its supplies. For the USA, Russia accounts for only 16% and China 2%. Again, to summarize the results, I have highlighted China and Russia supplies because of the geopolitical and commercial tensions between them and the EU and the USA. For the EU, we observe that China and Russia appear 12 times with a share at least equal to 10% in European imports and 10 times in the US case, for a total of 15 inputs plus batteries and cells. It points to a high potential for disruption of the supply chain because of the geopolitical tensions between the EU and the USA on one side and China and Russia on the other side. The importance of China and Russia is underestimated in my results because some countries import raw minerals from them for processing and later export to the EU and the USA. Russia produces about 10% of the world's nickel supply and is the second largest cobalt producer. To give just one example, the invasion of Ukraine drove the nickel price to double its 2021 level, and cobalt has followed soon. To summarize once again my results, what dominates is the dependence of the USA and China. What dominates is the dependence of the USA on China for some raw minerals such as graphite, nickel, cobalt, and together with Russia for processed materials such as refined lithium, fluorides, and alkali. The EU is also very dependent on China for refined lithium, fluoride, and alkali, and on cobalt oxide and hydroxide. It has also a high dependence on Russia on lithium oxide and hydroxide. So now that we know the high degree of dependence of the EU and the USA, let's turn to the second aspect of my presentation, which consider whether it is possible to reduce this high dependence by relocating at least part of the supply of these minerals and materials in the EU or in the US by developing sustainable onshore mining, which is an option in which many hopes are placed. In particular, you find different reports, such as the one published by McKinsey and Company, which are rather optimistic about the possibility to relocate these supplies and about the possibility to explore, to use technical innovation to make mining sustainable on an environmental and social point of view. Well, there are some room of maneuvers to reduce the use of cobalt and nickel to some extent, but there is no possibility to drastically reduce the use of lithium, which shows that although there are some possibilities, the hypothesis of replacing a substantial share of imports by local production should not be overestimated. Well, let's take two examples to see that in practice, the possibility to relocate these supplies by local production is in fact very complex. So the first example I want to detail is the case of the Jadar Valley in Serbia, which is very rich in lithium. And since 2020, Rio Tinto, one of the major global mining companies, with the support of the government of Serbia, has decided to purchase land and houses in this valley to then start produce lithium from the extraction of the so-called jadarite ore, which is a composite rich in lithium. So this purchase of land has created ghost villages and transformed this rural landscape into areas that look war-torn. 22 villages and around 20,000 inhabitants would see their life completely change because of the air, land, and water pollution. The local protest in a region known for its fierce nationalism turned national, and in the spring of 2021, the whole region was covered with no to lithium, yes to life signs. In the fall, blockades paralyzed the traffic on highways, and people marched in the streets of Belgrade, chanting that Serbia is not for sale. The government, which had planned to pass a law on expropriations, backpedaled quickly, announcing first the suspension and then the cessation of Rio Tinto's projects. So this is an example of what the EU calls the reluctance of the European population towards mining in a report published in 2021, because the extraction and refinery of the minerals needed for the production of batteries is energy intensive, uses a lot of water, and water, as you know, is becoming scarce in Europe because of climate change and because this so-called sustainable mining is still highly polluting. Now, let's turn to the USA to see the prospects of sustainable onshore mining. The same issue arises in the USA, where critical materials are sparking a mining boom. According to the US Geological Survey, the USA holds about 8 million tons of lithium, putting it in the top 5 most lithium-rich countries in the world, although today the USA produces only 1% of global production of lithium. So there is a huge potential which is still not explored, and this is why many mining companies are attracted by this potential, and now that prices of lithium are high and will stay high for a long time, they want to develop the production of lithium in the USA. Yet mining lithium and other metals in the USA face formidable difficulties, and I mentioned only some of them. 97% of America's nickel reserves, 89% of copper, 79% of lithium, and 68% of cobalt are found within 35 miles of Native American reservations. Lithium Americas plans a mine at Thacker Pass in northern Nevada, which is a place of memorial for local Indian population. Ioneer USA Corporation wants to build a large mine in southern Nevada, 500 kilometers far from Los Angeles, which may raise some environmental issues. And Piedmont Lithium in North Carolina plans to exploit the US largest deposit of spodumene ore, a mineral that can be processed into lithium, and Piedmont Lithium has already pledged to sell this ore to Tesla. All these projects face local opposition from the population who live in the surroundings, and also environmentalists who argue that the clean energy transition cannot build on dirty mining. The outcome will be decided by local and national politics. This is a very complex issue. I don't have time to detail all the complexities of developing mining in the USA, but let's say that it is highly uncertain, and the possibility to reduce the dependence on China and Russia by developing local mining is far from being certain. In conclusion, I just want to say that the resistance from the local population in Europe or the USA to these mining projects should not be underestimated, and this is why many onshoring projects are also risky, and we should not underestimate the difficulties that needs to be overtaken, simply because many of these projects do not take seriously into account the social and environmental impact of mining. Sustainable mining has still yet to prove that it is for real and not just greenwashing. This selected example shows that the rise of a mass electric vehicle market cannot avoid a critical reflection on its purpose. How to reduce geopolitical risk and produce the huge quantities of needed ore without worsening the carbon balance and degrading the environment? Is it possible to sell ever more electric cars and meet the Paris agreements? These questions are for the moment without response and deserve further investigation. I will stop here, and I thank you for your attention, and I hope to discuss these questions during the session that will be dedicated to this question. And I'm looking forward to meet you online and discuss these questions. Bye-bye.